Now, what is the relationship of the connection to the metric? In differential geometry, it's very simple, well known. And we can see it, for example, let me write these 1 over r things that I spoke about. These are connecting coefficients. How do they come out of the metric? So if we take, let's say, an ordinary metric for flat space in Cartesian coordinates, looks like this. Again, no space-time, no curvature, nothing, just ordinary flat. If I write the same thing in curvilinear coordinates, all right, I'm going to get something like dr squared plus r squared sine squared theta plus r squared d phi, whatever, right? Now, once I introduce these things, the r squares and the sine thetas and so on, they're going to show up in these connections. We know that the connection coefficient is 1 over r. The way to get it from the metric is simply you take, let's say, g theta theta prime over 2 g theta theta. Let's do that. G theta theta is r squared or r squared sine squared. Take the derivative with respect to r. So you get the 2r over here, 2r sine squared over 2 r squared sine squared. The sine cancels out, right? You get the 2r over the r squared, and you end up with 1 over r. 2r over 2. See that? It's simple math. Okay? This g prime, this derivative is 2r, divided by twice the thing itself, so it's 2r squared. The 2 cancels out, and you have r over r squared, you just get 1 over r. Sine the same thing over here. This becomes 2r over 2r squared, you just get 1 over r. All right? This is the connection coefficient, gamma r theta. So in differential geometry, one learns how to find the connections given the metric. Simple flat space metric. Given the metric, you do the derivative over the thing itself. There are other connections also. Sometimes you have to do g theta theta prime over g or r, or over g phi phi. I'm not going to get into them. Okay, basically, we're just going to look at this thing. It's like g prime or g prime over 2. Like a gradient, something like a gradient or a derivative.